A viscous flow is one in which the effects of viscosity, thermal conduction, and/or mass diffusion are significant. As a particle moves about in space, it carries with it its momentum, energy, and mass, which is basically its identity. Viscosity is due to the transport of momentum and becomes significant wherever there are large velocity gradients within a flow. Thermal conduction is due to the transport of energy and is similarly important in regions of strong temperature gradients. Mass diffusion is due to the transport of identity and comes about in regions of strong concentration gradients. In subsonic flows, thermal conduction and mass diffusion are ordinarily insignificant. As such, our treatment of viscous flows will focus on flows with strong velocity gradients. Here's something to think about. Why do golf balls have dimples? Well, hopefully to make them travel farther. Well, why then don't we add dimples to airplane wings? We want them to travel farther. We'll soon see that aerodynamic properties of blunt objects like the golf ball are different than the aerodynamic properties of streamlined objects like airplane wings. It turns out shape matters. If we neglect viscous effects and assume the flow is inviscid, the math will tell us the drag is zero. D'Alemberts proved this in 1752. But it was a paradox because observations in everyday life contradicted zero drag. When we assume inviscid flow over a streamlined object, we get good predictions for lift, but the drag is still zero. The next few slides will show how people in fluid dynamics model inviscid flow around a cylinder. If one knows the stream function, they can then plot streamlines, which represent the trajectories of particles in a steady flow. The stream function for flow around a cylinder can be built by summing models of uniform flow with velocity u infinity and a doublet, which in fluid flow is due to a source-sink combination. The end result is the equation in the yellow box. The stream function psi is u infinity times little r times sine of theta times the quantity 1 minus capital R squared over little r squared. Once we have the stream function, we can determine the radial and tangential velocities by differentiating it. On the surface of the cylinder, where little r is big R, in other words, the radius of the cylinder, the model tells us the flow does not cross the cylinder shell. That is, the radial velocity is zero. The tangential velocity has four interesting points. When theta is 0, or 180 degrees, we get stagnation points. When theta is plus or minus 90 degrees, the flow is at maximum velocity, which is exactly twice the free stream velocity. Cool, this matches our intuition. Knowing the surface velocities, we can then use Bernoulli's equation to calculate pressures acting on the surface. In aerodynamics, we prefer non-dimensional coefficients when possible. So the coefficient of pressure becomes 1 minus 4 times the sine squared of theta. With this equation, we can create a pressure map. Students often get confused when dealing with sine waves. Yes, they have amplitudes and periods, but this function is not 4 times the sine of theta. It's 1 minus 4 times sine squared theta. So it's not symmetric about the x-axis. The pressure map has large areas of negative pressure. That just means the pressure vectors are radiating out of the cylinder. The small areas of positive pressure, where the vectors are pushing in on the cylinder, are within plus or minus 30 degrees of the flow direction. Without any analysis, you may have thought pressure would have transitioned from positive to negative at plus or minus 45 degrees, and that their representative pressure areas would be about the same size. Sometimes intuition is correct, and other times it's wrong. This is what real or viscous flow around a cylinder looks like. From the inviscid analysis, the forces in the x and y directions would have canceled, leaving no lift or drag. But when you sum the forces in the x direction of the actual pressure map, you get a net drag force in the same direction as the flow. To understand why shear stresses exist, consider a shear flow. The graph shows a 2D velocity profile that varies in the y direction near the surface of the body. As such, a velocity gradient exists in the y direction. Because of the velocity gradient, the fluid above the plane AB is moving faster than the fluid below the plane, producing scrubbing or friction between the fluid layers. As air molecules immediately below plane AB intersect with those immediately above plane AB, they impart negative momentum, which imposes a retarding shear force on the upper layer. Conversely, as air molecules immediately above plane AB interact with those immediately below plane AB, they impart positive momentum, which imposes an augmenting shear force on the lower layer. Due to the rate of momentum exchange of the fluid molecules, a tangential force is exerted on plane AB. Furthermore, if the relative velocity between adjacent fluid layers increases, then the shearing force likewise increases, and vice versa. Viscosity is a measure of a fluid's resistance to shear. There is a relatively small region adjacent to the body where the effects of viscosity or friction must be taken into account. Called a boundary layer, the concept was introduced by Ludwig Reynolds in 1904. Outside this region, the flow field can be reasonably assumed to be inviscid or frictionless. Boundary layer thickness can vary from millimeters to inches on an aircraft. For ships in the water, the boundary layer can be as large as several feet. Within a boundary layer, velocity gradients are severe. The flow is retarded due to the presence of the body. From our previous discussion, this implies viscous effects are important. A boundary layer profile describes how the flow velocity changes in a direction normal, in the y direction is shown, to the surface of the body. Note that the velocity is zero at the surface. This is called the no-slip boundary condition. Sometimes the subscript W for wall is used to denote the surface boundary conditions. The effect of friction between the air and the body diminishes in the y direction. Hence, the velocity increases through the boundary layer in the y direction until eventually the presence of friction is no longer felt and the velocity gradient approaches zero. The boundary layer thickness, delta, is the height above the surface where the local free stream velocity is essentially reached. An important characteristic of boundary layers is that for thin boundary layers, static pressure at the top of the boundary layer is transmitted unchanged to the surface. Said another way, the static pressure is constant throughout the height of the boundary layer. Dynamic pressure Q decreases in the boundary layer as you descend to the surface, since velocity is decreasing. Thus, total pressure also drops as you descend into the boundary layer until it has the same value as the static pressure at the surface. We always see a loss of total pressure in the presence of friction. The reason this is so important is we are able to perform calculations in the inviscid region to get the pressure distribution over the body. Then, since the static pressure is transmitted to the surface, we will still get correct results for lift when we integrate the pressure distribution over the surface using the pressures found in the inviscid region. Two types of boundary layers exist: laminar and turbulent. A laminar boundary layer is characterized by smooth and regular streamlines. The velocity gradient has very orderly layers like laminated wood. In contrast, a turbulent boundary layer is random, irregular, and some even say tortuous. The boundary layer goes through a transition region before it finally becomes turbulent. But even in the turbulent region, there's still a thin laminar sublayer on the surface. The average velocity profiles for laminar and turbulent boundary layers are markedly different. First, a turbulent boundary layer is thicker than a laminar boundary layer under the same conditions. So delta for a turbulent boundary layer is greater than delta for a laminar boundary layer. Second, the turbulent boundary layer has a fuller profile with higher velocities near the wall. This has a very important implication. Higher velocities near the wall means the velocity gradient at the wall is higher for a turbulent boundary layer. It follows then that the shear stress at the wall is higher for a turbulent boundary layer. We'll see later that this implies a higher skin friction drag for a turbulent boundary layer. Turbulence is one of the great unsolved problems. Sir Horace Lamb said in 1932, "I am an old man now, and when I die and go to heaven, there are two matters of which I hope for enlightenment. One is quantum electrodynamics, and the other is turbulent motion of fluids. And about the former, I'm rather optimistic." The legendary Richard Feynman, who was himself largely responsible for explaining quantum electrodynamics, famously described turbulence as the most important unsolved problem of classical physics. So what are the factors affecting boundary layers? The first is density. Increased density gives a thinner boundary layer. The second is velocity. Increased velocity also gives a thinner boundary layer. The third is the distance along a surface, or x. Increased distance results in a thicker boundary layer. And the fourth is viscosity. Viscosity is defined as the resistance to gradual deformation by shear stress or tensile stress. It opposes relative motion between two surfaces moving at different velocities. It's the friction between the molecules of fluid. Increased viscosity gives a thicker boundary layer, and like other properties in aerodynamics, viscosity depends on temperature. But unlike motor oil, where we typically associate higher viscosity with cold temperatures, the viscosity of air goes up the hotter it gets. Students often get confused on this trend. After all, we're used to motor oil. The oil is thick at cold temperatures. Cars need to warm up to loosen things up. But if they get too hot, the viscosity will break down, causing wear on engine parts. We've all heard the television commercials. Air goes against this intuition. The viscosity goes up the hotter it gets. We can use Sutherland's formula or use a table that lists viscosity along with other standard atmospheric properties. So boundary layers are affected by density, velocity, distance along the surface, and viscosity. So question, can we predict the layer thickness and determine whether it's laminar or turbulent? Well, this is a bit tricky, but luckily Osborne Reynolds helped us ease the complexity. Reynolds number is a very important parameter in aerodynamics and has many applications. It is used to determine boundary thickness and predict whether a boundary layer is indeed laminar or turbulent. It's also used for similitude, matching a scaled model to the actual article. Physically, it represents the ratio of inertial forces to viscous forces. An aerospace or flight test engineer should know this physical definition. A high Reynolds number implies inertial forces dominate viscous forces. A low Reynolds number implies the opposite, that viscous forces dominate inertial forces. The equation for Reynolds number is shown. It's basically the density times the velocity times the distance along the surface, all divided by the viscosity. What we just defined was the local Reynolds number. For an aircraft, it is common to refer to the chord base or characteristic Reynolds number. This is the Reynolds number at the trailing edge of the airfoil, where x equals c bar, the chord length of the wing. For typical aircraft applications, the chord-based Reynolds number is usually relatively high, on the order of 10,000 to 100 million. There's a third Reynolds number called the critical Reynolds number. This uses the x distance where the flow transitions from laminar to turbulent. So now we're back to answering a tough question. Where does turbulent flow start? Unless you've run a controlled experiment and measured the answer, the next best approach is to assume a critical Reynolds number of 500,000 and then back out the x distance based on the velocity and the viscosity. As an aerospace or flight test engineer, it's always good to have a ballpark idea of what to expect a parameter to be, right? Our craft is to know if something is about right or hey, something's a little bit off here. Unfortunately for me, I've never been able to get a feel for a Reynolds number. I have a hard time visualizing the difference between a Reynolds number of 2 million and one that's 60 million. That being said, let's go ahead and calculate one. We'll take an F-16 flying at 550 knots at 3,000 feet. Its mean aerodynamic chord is 11.4 feet. We can either use a table with viscosity, or some tables have what's called kinematic viscosity, nu, which is mu over rho. Either way, the key rho in the table will be the altitude, which for this example is 3,000 feet. All engineers need to be cognizant of units. I'm assuming you can translate knots into feet per second. In the end, Reynolds number is a non-dimensional parameter, so the units need to all cancel. For this example, we get a Reynolds number of 62,617,554. So if we want to model an F-16 in a wind tunnel under these flight conditions, we need to match this Reynolds number. To show you how confusing Reynolds numbers can be, I've plotted 4 cases. Right away, you see that an F-16 can have about the same Reynolds number as an Airbus A380. The Piper Cherokee 6, flying at 5,000 feet, can have a similar magnitude Reynolds number, albeit slightly higher, than a Global Hawk flying at 55,000 feet. In the end, we have the equation. So we know we can get low Reynolds numbers with either small chord, low velocities, and high altitude. With a low Reynolds number, there's going to be significant friction. We can get a high Reynolds number with a large chord, high velocities, and low altitude. With a high Reynolds number, friction is less important. Using Reynolds number, theoretical and experimental results provide a simple means of estimating the thickness of a boundary layer as a function of the distance traveled from the leading edge. The equations shown are for a flat plate. Again, note the boundary layer thickness of the turbulent boundary is greater than the laminar. At this point, we need to go back to the big picture. What does all of this have to do with airplane performance? In flight test, we'll gather data to create the drag, which is derived from thrust or power required, versus airspeed curve. At this point, you may have heard phrases like the front side or back side of the power curve. Well, this is the power curve. It's the sum of induced drag and parasite drag. It's affected by density, velocity, distance along a surface, viscosity, basically the parameters that make up Reynolds number. Later, we'll cover induced drag and interference drag, but for now, we'll focus on the parasite drag component, specifically the profile drag contributions for skin friction and form or pressure drag. Skin friction drag is the drag due to shear stress caused by friction. As you might expect, the total skin friction drag, d sub SF, is a function of the surface area of the object and the free stream properties like density and velocity. We see the symbol capital S used often in aerodynamic analysis. Sometimes it's the projected wing area, which is basically the area of the shadow a wing makes on the ground. Other times, it's what's called the wetted area, which is the surface area that would get wet if the aerodynamic body were submerged in water. So make sure you understand which area is being used. Surface roughness obviously impacts skin friction drag, but even the smoothest surface generate skin friction drag. If you zoom in enough, a smooth surface will have some bumps. It can be shown that skin friction is directly proportional to the shear stress at the wall or the surface of the object. It follows that the higher the velocity gradient at the wall, the higher the shear stress, and the higher the skin friction. Therefore, turbulent boundary layers create more skin friction drag than laminar ones. Next, we'll examine form or pressure drag. When a particle moves from a region of high pressure to low pressure, it is called a favorable or proverse pressure gradient. Frictional forces resist forward motion, but pressure forces kind of pull it along, so the flow stays attached without any problems. Low to high pressure is called an adverse pressure gradient. Particle has both friction and pressure forces resisting its forward motion. The only thing keeping it attached is the momentum it had entering the adverse gradient. Eventually, it runs out of momentum and heads in a direction that's easier. In other words, it separates. Flow separation is different than transition. Recall that flow starts out laminar, then transitions to turbulent. But the turbulent region still has a laminar sublayer where velocities near the wall are still positive. Separation occurs when the velocity near the wall transitions through zero. After that point, flow can actually go backwards from the streamwise direction. In that case, there will be a resultant force in the opposite direction of the stream, and this is pressure drag. The consequences of flow separating over an airfoil are a drastic loss in lift and a major increase in drag. In order to decrease pressure drag, we need to delay flow separation. And there's several ways to do this. One primary means of delaying separation is by minimizing the adverse pressure gradient. This is accomplished by designing the proper shape. Sharp trailing edges are desired, no blunt objects. When a body is said to be streamlined, it means sharp trailing edges, and minimizing pressure drag is why it is done. The other primary means of delaying separation is by having a high energy boundary layer. There are several ways this can be accomplished. First, a higher free stream velocity will help. The higher velocity means the fluid elements in the boundary layer have more momentum, and they are able to stay attached longer. Boundary layer type also has an effect. Recall that a turbulent boundary layer has a larger velocity gradient in the vicinity of the wall than a laminar boundary layer. This means the fluid elements near the wall have more momentum. Therefore, a turbulent boundary layer will stay attached longer than a laminar boundary layer. Also, there are ways to energize a boundary layer in an effort to delay separation. Vortex generators are one example of boundary layer control devices. Others include tangential blowing, such as jet exhaust, or surface suction. This figure shows the effects of shape on flow separation. The top shows a flat plate perpendicular to the flow. This is basically the worst case. The wake separated flow is the largest. Next is the cylinder or sphere. It's better than the flat plate, but notice how when we add a fairing, the wake separated flow is reduced. The bottom housing results in an even smaller wake. You'll see these type of fairings and housings used on fixed gear general aviation aircraft. They call them pants or boots, depending on whether they're added to the struts or the wheels. Even the most aerodynamic airfoil will have separation at high angles of attack. In the stall and post-stall regions, lift is reduced and drag is increased. So now we're back to the original two questions we started this module with. Why do golf balls have dimples, and why don't wings have dimples? We have arrived at one of the great compromises of aerodynamics. A laminar boundary layer decreases skin friction drag, but increases pressure drag. A turbulent boundary layer is desirable to decrease pressure drag, however, it increases skin friction drag. Ultimately, the shape of the body dictates which type of drag, skin friction or pressure, is dominant. As you would expect, skin friction is dominant for thin bodies, while pressure drag dominates blunt bodies like the golf ball. This is why airplanes with sharp trailing edges have smooth surfaces. Skin friction dominates at low angles of attack, and laminar boundary layers are desirable to minimize skin friction drag. And this is also why golf balls have dimples. The dimples trip the boundary layer so it becomes turbulent, thus reducing the pressure drag, which is most dominant in this case. But we are starting to see some of these aerodynamic principles show up in not so obvious situations, like the turbine blades of a jet engine. Adding a dimple, depending on the Reynolds number seen by the turbine blade, may actually improve engine performance. Engineering in general involves compromises. This slide puts it all together for aerodynamics. But other design conditions and considerations exist. For example, flush rivets are more difficult to manufacture than standard rivets. Is it worth the effort of producing fairings like pants or shoes? How difficult is it for maintainers to work on tires, brakes, and gear if the gear has pants and shoes? And if you think boundary layers aren't important, just go talk to a propulsion engineer. In summary, we introduced viscous flow theory. We defined boundary layers along with laminar, turbulent, and separated flow. We defined a not-so-intuitive parameter called Reynolds number. We compared skin friction drag to form or pressure drag. We answered those two fundamental questions. Why do golf balls have dimples? And why don't wings have dimples?